All right, we finally made it to the very last section that we'll be covering in this class. It's 6.6 in your book, where we're going to talk about centroids. 6.6 in your book actually covers a lot of different applications of integration. I think it looks at a bunch of different contexts within physics, but we're just going to focus on one of them, this idea of centroids. And all centroids are, informally speaking, is kind of like the balance point. And what am I talking about? Well, let me start you out with some simpler cases. Suppose that we have a seesaw here, and on one side of the seesaw we have something that weighs 2, and on the other side of the seesaw we have something that weighs 3. And we have to make some kind of simplifying assumptions, so we're going to assume that the seesaw doesn't weigh anything at all, and that there's no friction, and that this 3 is a point mass, so it all lies at the exact same point, and this 2 is also a point mass, and we'll assume that those are equally spaced out. And then I ask you the question, which side of the seesaw is going to go down? And you're like, that's the easiest question you've asked all turn. Clearly, this side is going to go down because 3 weighs more than 2, so this gravity will pull this guy down. And that's absolutely right. And what I want to do in the second question is ask you something similar, except now I want to change things so that each of the point masses are exactly 2. Up here, one was 3 and one was 2. Here, they're both 2. And you're like, wait, if they're both 2, won't it balance? Well, no, because now one of them is closer into the middle of the seesaw and the other one is further out from the edge of the seesaw. And then I ask you the same question, which side of the seesaw will go down? And I think you can convince yourself that this side of the seesaw will go down. That's a result of torque. But you can convince yourself of that pretty easily if you take, like, I don't know, a ruler and try to balance 2 equal weights on each side of the ruler, but don't have your finger in the middle, put your finger way off to one side, well, the other side is going to fall down. So I think both of these are pretty apparent. I'm not going to justify these. I'm going to take these as a given. Where things get interesting is when the weight differs and the distance differs. So if this side weighs more, but it's closer into the middle, and this side weighs a little bit less, but it's further out from the middle, which of those two opposing forces will win out? Which side of this seesaw will go down? And I don't think it's at all obvious which side of the seesaw will go down. I mean, you can take a guess if you want, but if you know something called the law of the lever, something that goes all the way back to ancient times, Archimedes, I believe, is credited with this. What it tells you is that all you have to do to figure out which side will go down is multiply the mass times the distance. So this 2 times this 7 gives me 14. And this 3 times this 3 gives me 9. And since 14 is greater than 9, that means this side will go down. And you're like, all right, cool, I think I understand all that. I think I can always figure out which side of the seesaw will go down. Well, bad news, we're not trying to figure out which side of the seesaw will go down, but we're trying to do something very related to that. Let's get away from this seesaw analogy and go down to a number line. So we have this number line, and at some point that I'm going to leave as just x1 on this number line, there's a mass, and we'll call it m1. And at some other point on the number line, I'll call it x2, there's another mass that I'll call m2. And suppose I ask you the question, where is x bar, where x bar is understood to be the balancing point? Where is the center of mass of this system? We can use similar logic to what we did up here with the seesaw, where we figured out which side would go down by multiplying the mass and the distance of each of the 2 points. We can do that same thing here, except instead of figuring out which one will be bigger, we could set those equal to each other to figure out the balance point. What I'm saying is if x bar is the balance point, it must be the case that the distance from x1 to x bar, which I can represent as x bar minus x1, times m1 is the exact same as the distance from x2 to x bar times m2. The distance times the mass equals the distance times the mass, then this thing will balance. Note that in my picture it's x bar minus x1 and it's x2 minus x bar because x2 is to the right of x1, but this generalizes and you don't have to worry too much about the order that those are in. At any rate, if I wanted to solve for x bar, well, let's see, maybe I'd get rid of the parentheses first by distributing m1 and m2 through. And now I have 4 terms, and 2 of those terms have x bars in them. So if I collected all my terms with x bars on the left-hand side of the equation, so adding this to both sides and then adding this to both sides, that would give me to this step. And now that I have all my x bars together on the same side of the equation, I could factor an x bar out from the left-hand side of the equation, yielding this expression, which I could use to solve for x bar if I just divided both sides by m1 plus m2. I could use this formula to figure out where I would have to have the balance point be if I had a weight of 2 on one side and a weight of 3 on the other side. All I would need to know are the positions of those weights, 2s and 3s. I could put the 2 weight wherever I want. All that's important is that these 2 guys are separated by a total distance of 10. So maybe I call this position 0 and call this position 10. Then I would have the first mass, which is 2, times the first position, which is 0, plus the second mass, which is 3, times the second position, which is 10, divided by the sum of the 2 masses, which is just 2 plus 3. So I get 30 over 5, I get 6. What I'm saying is, if I think about this as being at 0 and I think about this as being at 10, then x bar would be equal to 6. Oh yeah, that works out really nicely, right? If the balancing point is at 6, 6 times 2 gives me 12. And if this is at 6 and this is at 10, that distance of 4 times this 3 also gives me 12. It looks like that would work. And so maybe you're like, all right, this formula doesn't seem so bad. All I have to do is take each of the different points and multiply their masses and their positions, and then add those all up, and then divide by the total mass. And that's true, but what we want to do is generalize this a little bit more. Two things. The first thing is we don't want to limit ourselves to just 2 points. What if there's a point here, a point here, a point here, and a point here? Well, it turns out that something almost identical to this formula will work. All we would do is instead of just adding m1x1 and m2x2, we'd add on m3x3 and m4x4 and so on. And down in the denominator, instead of just having m1 plus m2, we'd have m1 plus m2 plus m3 plus m4 and so on. What I'm saying is a more general formula, if you have n points as opposed to just 2, would be this guy right here. And I won't prove that, but the logic is kind of the same as what we did before down here. And is really just a consequence of this law of the levers thing. And you're like, okay, so I just have to use this formula and then I'm done? Well, not quite. What we're going to do is not only are we not going to limit ourselves to just 2 points, we're also not only going to limit ourselves to the x-axis. So what if this were my system, right? What if I had 2 different dimensions here and I had 3 different points, a point here, a point here, and a point here. And those points weighed 1, 4, and 5 respectively. Now it's a 2-dimensional problem and I ask you the question, where is the center of mass? The way you can think about that is if our coordinate axes here, the XY plane, were a weightless sheet of glass, and you put one weight over here that weighed 5, one here that weighed 4, and one here that weighed 1, where would you put your finger underneath that sheet of glass if you wanted to balance it? And you're like, well, I certainly wouldn't put it over here because if I tried to balance here, all of the weights would be kind of down and to the left of where my finger was, and this thing would tip over. And you wouldn't have it over here because then it would tip in this direction. So it must be kind of somewhere in the middle, but kind of somewhere in the middle isn't good enough for us. What we want is one specific point. And you might be a little intimidated here and you're like, oh no, this is going to be really hard because what I'm going to have to do is find each of these different masses and multiply it by their distance from the center point. And the distance in 2 dimensions might be really challenging. And it would be challenging if we handled it that way, but there's a nice little trick that we can do. What we can do is completely ignore the y dimension and just find the balance point in the x direction. And then that will be the x coordinate of our center of mass. And then we can completely ignore the x direction and just focus on the y direction and figure out the y coordinate of our center of mass. And then once we have the x and the y coordinates of our center of mass, we have the answer to this question. So we don't really have to deal with it 2 dimensions at a time. We can deal with each dimension individually. And this formula that we derived before will work out perfectly to figure out the x coordinate of our center of mass. And the formula that we'll need for the y coordinate of the center of mass will be almost identical to what you see here. We'll just change all the x's to y's because we'd use an argument almost identical to what we do here. We just rotate the picture 90 degrees. What I'm saying is we can use these 2 formulas to figure out the center of mass of this system that we have down here. To figure out the x coordinate of the center of mass, what we want to do is look at these points but completely ignore their y coordinates. Just notice that this guy has an x coordinate of -3. Yeah, its y coordinate is equal to 2, but we won't need that for this formula. Similarly, this point has an x coordinate of 1, which will be relevant, and a y coordinate of -2, which will not be relevant. And this guy here has an x coordinate of 4 and a y coordinate of -1, the 4 being relevant, the -1 will not be relevant. So if we plug that into this formula that we have up here, where we take m1 times x1, maybe calling this our first point, our second point, and our third point, I would take this 5 times this -3, and then I would add to that m2 times x2, so 4 times this 1. And then I would add to that this mass times this x coordinate, m3 times x3, so 1 times 4. And then I would divide this thing by the total mass of the system, m1 plus m2 plus m3, so 5 plus 4 plus 1. And if I calculate this, I get -15 plus 8, so I get -7 divided by 10. I can do the same thing to figure out the y coordinate of the center of mass. I'm still multiplying these masses 5, 4, and 1, and I'm still dividing by the sum of these masses, the 5, the 4, and the 1. But what I'm changing is now it's not the x coordinate that I'm interested in, it's the y coordinate that I'm interested in. So for this first point, the y coordinate is a 2. For this second point, the y coordinate is a -2. And for this third point, the y coordinate is a -1. I get 10 minus 8 minus 1 more, so I get 10 minus 9, I get 1 over 10. What I'm saying is if you wanted to balance this, your x coordinate would be at -7/10, so roughly here, and your y coordinate would be at +1/10, so roughly here. The centroid of this system is at -7/10, +1/10. And that's what we need to figure out in this video. and you're like, wait, there's something missing. This is a calculus class. You just did several examples talking about seesaws and balancing points and stuff, and you didn't use any calculus at all. Right, in the finite case, we're not going to use calculus. But in the infinite case, which you'll see in the next video, we do use calculus. And you're like, why'd you waste all this time on the finite case? Because the formulas that we use for the infinite case will get derived from these formulas that we use for the finite case. So like we do in a lot of applications in this class, we kind of understand things in the finite case first, and then see how we can apply that knowledge to what we know about calculus and use some integrals.